Thank you very much for the introduction. So this is the title of my talk. But before getting there, I'd like to have a few words about IPMU. So when IPMU started in 2007, I was a postdoc in the United States. Everybody there told me that Japan still knows how to fund basic science. Great! Well, since then I learned that the reality is much more nuanced and complicated. Anyway, I visited IPMU for the first time on December 2008 to give a seminar. Back then we didn't have the nice building we now have. So as you know, we just had prefabs, right? And I Googled a photo from those days and I found a blog by a former postdoc called Confessions of a Classless American Goon. So this is a prefab, and if you go in front of the door, you have the logo of IPMU, and the blog says the Institute placard had Scotch tape involved. So that was 9 years ago, and how we changed, right? So 10 years later, I'm a faculty member at the IPMU. I've seen how IPMU grew over the years. This makes me very nostalgic. And here we are having this nice 10th anniversary workshop. Well, but birthday parties are for children, and indeed, IPMU is still in its childhood. So IPMU, I hope IPMU to grow up further and become mature without too much problems to become middle-aged, right? And nobody feels the need to do an anniversary workshop because IPMU will be so established, right? You don't have to feel the need to do this. So let me come to the meat of the talk. I tried to make a talk light-hearted, and so the title is What is Quantum Field Theory? You've heard already about quantum field theory many times during this workshop. And let me start with a simple answer. I don't know. Right? So the next slide says the end. Thank you very much for listening. Thank you very much. Of course, this is joking. The time is, running late, so I can really stop at this point, but if I may continue, I will. Right, so what is a quantum field theory? It describes quantum property of fields. So here, a field is not the mathematical field, but a field is anything that is extended along the space and time, right? So examples are electromagnetic field, electron field, and you can also think of vibrations of a crystal as a field, right? And prototypical quantum field theory is the quantum electrodynamics. This describes the quantized electromagnetic field interacting with electrons and other charged particles. And it was established around 1950s. So it's more than half a century ago. And since then, there has been a steady progress in our study of quantum field theory in general. For example, by now, we know that our world, at the most microscopic level, which is experimentally accessible, is described very well by a quantum field theory called the Standard Model, established theoretically in the 1970s. Its final piece, the Higgs boson, was confirmed experimentally 5 years ago, and both high-energy theorists and experimentalists are looking for physics beyond the Standard Model. But this is one example of a quantum field theory. Quantum field theories are not just for high-energy physicists. It is also for condensed matter physicists. For example, physics at the second-order phase transition is often described by something called conformal field theories, which form a certain subclass of quantum field theories. These days, there are something else which is very popular, which is called symmetry-protected topological phases. And I don't have time to explain what they are, but they are studied both in condensed matter physics and also in high-energy physics theory. They are also quantum field theories. So quantum field theories are very ubiquitous in theoretical physics, but this ubiquity is not surprising, right? Since by definition, quantum fields are just the quantum version of anything that are extended along the space. So due to its ubiquity, many people have worked on quantum field theories over its history of more than half a century. Theoretical predictions agree very well with experimental results. One extreme example is the measurement and computation of anomalous magnetic moment of the electron. So both experimental result and the theoretical results are so precise, and they agree very well. So if you hear for the first time about these very nice agreements between theory and experiment, you might say, well, then the quantum field theory needs to be already very well established, and nothing would be remaining to be done, right? However, even with this impressive agreement, I say we don't yet know what's the correct framework to study quantum field theories. This is in contrast to the situation for quantum mechanics or general relativity, for which I say we know the correct frameworks, right? So let me try to say why I think this is the case. So IPMU contains both mathematics and physics, right? So please imagine a situation of a physicist in front of a mathematician and trying to explain what these physics subjects are. What is the quantum mechanics? Can I explain it in a sentence to a mathematician? Yes, it's a study of unitary operators acting on the Hilbert space. Good. How about the case of general relativity? It's a study of differential equations satisfied by the Riemann tensor of a Lorentzian metric on a manifold. Good. Nice one sentence. Not bad. But then, what is quantum field theory? As a physicist, I think I know what it is. I've been studying quantum field theories for, I don't know, at least 15 years, maybe approaching 20 years. But unfortunately, I don't have a way to explain it in a sentence to mathematicians. And I believe it's not just a problem about me. So is there any physicist out there who can just explain it in a sentence? So, yeah, please.
It's a mathematical framework which contains both special relativity and quantum mechanics. The job of mathematician to show that it's not an empty.
I think that's a rather one-handed, how should I choose a polite adjective? But I mean, in condensed matter applications, special relativity part of QFT is not important. So, well, that's understandable. It's understandable that Oguri-san started the sentence that way, because, I mean, just both of us came from high energy physics, but these years I talk often with condensed matter physicists, so I try not to use that kind of introduction, but thanks for trying. Because if somebody could answer, I was thinking of just changing the places and keep that person to continue the talk. But anyway, so many people try to formulate mathematically some small part of what they knew about quantum field theories. Some from 20th century are, axiomatic QFT and algebraic QFT. Another is called vertex operator algebras. There are things called topological quantum field theories. But in none of the frameworks from the 20th century, we can express the computations that led to this impressive prediction about anomalous magnetic moment of the electron. So the problem is that the framework of axiomatic QFT is too broad and generic to carry out this particular computation. And also the frameworks of vertex operator algebras and topological QFTs are unfortunately too narrow and doesn't include the real quantum electrodynamics. That said, the fact that physicists can compute this value to this great precision means that explicit method to compute this quantity is very well explained in textbooks, right? So you might think that the only remaining problem is to formulate that computational method. Well, this mathematical reformulation is actually being done by Costello and collaborators under the name of factorization algebras, and I think it's very important. But suppose this mathematical reformulation completes. Does this answer my original question, what is a quantum field theory? I don't think so. And I'd like to illustrate why I think so during the rest of the talk. So using my personal experience. A big topic in my area is supersymmetric quantum field theories. Supersymmetry allows one to transform the bosons, such as photons, etc., and to fermions, electrons, and some others. And I'm interested in its theoretical structure. There can be quantum field theories that can have multiple supersymmetries. Today I'm only talking about 3 + 1 dimensional quantum field theories. And so if there are multiple supersymmetries, for example, if there are 2 supersymmetries, it is called an n = 2 supersymmetry. If there are 4 supersymmetries, the theory is called n = 4 supersymmetry, and so on. So how many supersymmetries can a 4-dimensional quantum field theory have? Well, that's a topic covered very often in the first chapter of a textbook on supersymmetry. And the standard answer has been as follows. There are n = 1 supersymmetric theory, there are n = 2 supersymmetric theories, and there are some n = 4 supersymmetric theories. And that's it. Well, I don't have time to explain why there can't be more than 4, but everybody who looks at this list notices a big hole. What happened to n = 3, right? So what textbook says is this. So this is the schematic picture of the space of quantum field theories. There are lots of quantum field theories. The standard model is 1. And there are some supersymmetric theories. There are a lot. There are some number of n = 2 supersymmetric ones. There are a fair number of them. And there are a few n = 4 cases. But people say that there is no supersymmetric theories which is genuinely n = 3. So people say that if a quantum field theory has n = 3 supersymmetry, you can easily check that it has in fact n = 4. I myself wrote thus in a lecture note published in 2014 from Springer Fairlock. But this paper appeared on December 20th, 2015 with the title n = 3 4-dimensional field theories, where genuinely n = 3 theories were found using string theory. So was everybody just stupid, including me? Why were all the textbooks, including mine, wrong? So there are indeed some n = 3 theories. So let me explain why. Everybody in the audience, including mathematicians, should have learned Newtonian mechanics when they were in high school, or maybe not, maybe when they were undergrads. So the equations of motion of object attached to a mechanical spring can be written thus, right? But we then learn that equation of motion is not really the fundamental principle governing the mechanics. People learn that instead you should consider the Hamiltonian p² + x², from which you can derive the equations of motion. And then you learn that there's indeed another formulation which is called Lagrangian framework, where you start from the action and from which you can construct Hamiltonian equations of motion. And we are taught that Hamiltonian and Lagrangian frameworks are equivalent, right? And similarly, in the textbooks, textbooks currently available on the bookshelf of a bookstore or on Amazon on quantum field theories, it's often said that, well, quantum field theories have equations of motion, which you can write down And there are Hamiltonians generating time translation, translation along the direction x, translation along direction y and z. They are complicated. But they say that you can start from a Lagrangian of a quantum field theory, which is relatively simple and can be written down easily, from which you take the variation and get Hamiltonians and equations of motions. Richard Feynman even got a Nobel Prize for coming up with the Lagrangian framework for quantum field theories. But in the last several years, we learned that in fact, for many quantum field theories, Lagrangian descriptions are not available. We just have Hamiltonians, which are complicated, and equations of motion, which are also complicated. And you need to live with that. There's no Lagrangian involved. So the mistake, so now I can explain why did all the textbooks, including mine, mistakenly state that any n equals 3 quantum field theory should automatically have n equals 4 supersymmetry. Well, what happens is this. If you assume the existence of a Lagrangian, what you do to look for n equals 3 theory is this. You write down all possible n equals 2 supersymmetric Lagrangians, right? Then you look for any theory that has more than n equals 2 supersymmetry. And you just go over them one by one. And you find that, well, there are just n equals 4 and never anything properly with n equals 3 supersymmetries. But this derivation assumes the existence of a Lagrangian, right? So there can be n equals 3 theories without Lagrangians. And indeed, there are. So that paper from December 2015 doesn't use the existence of Lagrangian as the starting point. Instead, they constructed the n equals 3 theory inside string theory, some strongly coupled version of string theory. So that's basically the end of my talk, but let's revisit the main issue from a slightly different perspective. So this is the old but standard way to approach the study of a QFT. So you start from a Lagrangian, and that describes a QFT. That's the standard thing you learn in the textbooks. Since 20 years ago or something, it is common, thanks to the works by Zeiberg and Witten, it is common to have a situation, slightly complicated situation like this. So you can start from a Lagrangian 1, or you can start from a Lagrangian 2. Two different Lagrangians, however, give rise to the same QFT. This has been called the duality. But the things don't stop here. Of course, there can be more than 2 Lagrangians that describe the same QFT. Lagrangian 1, Lagrangian 2, and Lagrangian 3 can describe a single QFT, right? So some call this a triality. Of course, things don't stop here either. So there can be many Lagrangians, Lagrangian 1, 2, to Lagrangian n, where n is a natural number. This can be called an n-ality. I don't think anybody uses that word. People just call it a duality. But here, the important point is that natural numbers start from 0, not from 1. So you just put 0 to n, and voila, you have this situation where there's no Lagrangian, but you have a QFT. So having no Lagrangian is an example of the n-ality, where n equals 0. It's an extension of the concept of the duality. So zero-ality, unality, duality, right? Triality, and n-ality, and zero-ality, right? So this is the story of non-Lagrangian theories I'm advocating for the last few years. So let me conclude. So basically, all the textbooks on quantum field theories out there use an old framework that is simply too narrow in that it assumes the existence of a Lagrangian. So this is a serious issue because, well, when you try to come up with a theory beyond the standard model, right? People habitually start by writing a Lagrange, right? But that assumption might be actually putting a too strong an assumption as a starting point. So I think we need to do something. And that's the end of my talk. Thank you very much.